Welcome to all of you, dear students. Now we discuss Unit 4 2022 Advanced Mechanics Semester 6. Question paper 2022 Advanced Mechanics Unit 4. Question 5a. What is a canonical transformation? So that the transformation capital P equal to half P square plus Q square, capital Q equal to tan inverse Q by P is canonical. Canonical transformation. Suppose that Qk and Pk are the old position and momentum coordinates, and capital Qk and capital Pk are the new positions and momentum of this Qk. Let these coordinates be related by the following transformations. Capital Pk equal to, capital Pk is the functions of P1, P2, Pn, Q1, Q2, Qn and time t. Capital Qk is the functions of P1, P2, Pn, Q1, Q2, Qn, t. If there exists a new Hamiltonian, capital H dash is the function of capital Qk, capital Pk, t, and that means capital Q1, capital Q2, capital Qn, and capital P1, capital P2, capital Pn, and time t, such that capital Pk dot equal to minus del del capital Qk H dash, and capital Qk dot equal to del del capital Pk H dash. Equation 2. K equal to 1, 2 up to n, where H dash, capital H dash equals to summation K equal to 1 to n, capital Pk, capital Qk dot means the derivative with respect to time t, minus capital L dash functions of Q, Qk dot, t. That is Q means Q1, Q2, capital Qn, and Qk dot means capital Q1 dot, capital Q2 dot, capital Qn dot, and time t. The new Lagrangian L dash substituted in the Hamilton's principle is the delta integration L dash dt equal to 0, gives the correct equation of motion in the new coordinates capital Pk, capital Qk. Then the transformation 1 are known as canonical or contact transformation. Next part. So that the transformation capital P this and capital Q is equal to this is canonical. The given transformation will be canonical if the expression P dq minus capital P d capital Q is an exact differential. Now, d capital Q equal to P dq minus Q dp by P square plus Q square, because this capital Q equal to tan inverse Q by P. So tan inverse Q by P, this equals to P dq minus Q dp by P square plus Q square. And P dq minus capital P dq is equal to P dq, and this P means this capital P equal to this 1/2 of P square plus Q square, tan inverse 1 by 1 plus Q square by P square. And this, so after simplification, we get this d of half pq. This d of half pq, so this is an exact differential, df. This f is a genetic function equal to half pq. Hence, the given transformation is canonical. Now, if capital P equal to this and tan q equal to small q by p, then capital P equal to half p square, and the value of q square from this, so p square into tan capital Q square. So we can find half p square sec square capital Q, and small p square equal to twice p, this sec cos square capital Q. So p equal to root over 2 capital P cos capital Q, and Q equal to P tan capital Q. So value of small p, this is equal to root 2p cos q tan q, that is equal to root 2p sin capital Q. Hence p equal to this and q equal to this. The generating function capital F equal to half pq. So putting these values of p and q, we get this, and this half capital P sin twice q. Alternatively, we can write this capital F is this half q square cot capital Q. So these are different forms of the generating function capital F. Next question, question 5b. So that the generating function for the transformation p equal to 1 by capital Q, q equal to p capital Q square is F equal to q by capital Q. So this p equal to 1 by capital Q. So capital Q equal to 1 by p and dq equal to minus 1 by p square dp, and q equal to p q square. So capital P equal to q by capital Q square, that is equal to q by 1 by p square, that is equal to q p square. Hence p dq minus capital P dq equal to this using 2 and 3. So we get an exact differential, this capital F equal to pq. This is the generating function. And putting the value of small p, this equal to 1 by capital Q. So we get a generating function, this q capital Q, this q by capital Q is a generating function. Next question, 5c. Derive the Hamilton-Jacobi equation for Hamilton's principal function S. Solve the Hamilton-Jacobi equation for the system whose Hamiltonian is given by h equal to p square by 2 minus mu by q. Hamilton-Jacobi equation for S. If we make a canonical transformation from the old set of variables qk pk to a new set of variables capital Qk capital Pk, then the new equations of the motion are pk dot equal to minus del del qk h dash and qk dot equal to del del pk h dash. Now, if we require that the transformed Hamiltonian h dash is identically 0, then h dash equals to 0, then from 1 we get pk dot equal to 0 and qk dot equal to 0. Hence pk equal to constant and qk equal to constant. Thus, the new coordinates and momenta are constant in time and they are cyclic. And the new Hamiltonian h dash is related to the old Hamiltonian h by the relation h dash equal to h plus del del tf, which will be 0 only if f satisfies the relation h q k p k t plus del del tf equal to 0, where h q k p k t is written for h, this qk means q1 q2 qn and pk means p1 p2 pn comma t. For convenience, we take the generating function f as this f2 type is qk pkt, then pk equal to del del qk f2. So 3 reduces to h qk del del qk f2 comma t plus del del t f2 equal to 0. Now the total time derivative of f2 is equal to dt of f2 equal to summation over k equal to 1 to n del del qk f2 qk dot plus summation over k equal to 1 to n del del pk f2 pk dot plus del del t f2. Here pk dot equal to 0, so this term is 0, and the del del t f2 equal to minus h, and from 5. So we get ddtf2 equal to summation over k equal to 1 to n pk qk dot minus h, this equals to L by 4. This equal to 4 pk means del del qk f2. So put this value of pk, and then f2 equal to integration L dt, this equal to s, action integral, where s is the familiar action of the system known as Hamilton's principal function in relation to the variational principle. Writing f2 equal to s, we get from 5, this equation is 5, so we write HQK del QKST plus del TS equal to 0, equation 7. This is known as Hamilton-Jacobi equation, which is a partial differential equation of first order in n plus 1 variables q1, q2, qn and t. Next, second part question. This question second part is this: solve the Hamilton-Jacobi equation for the system whose Hamiltonian is given by h equal to p square by 2 minus mu by q. So h equal to this and p equal to del qs. Hamilton-Jacobi equation for s is given by h q del qst comma del ts equal to 0, and by 1, and this h equal to this p square by 2 minus mu by q plus del st equal to 0, and this equal to this p equal to del qs, so this half del qs whole square minus mu by q plus del ts equal to 0. Its solution B, s equal to s1 is a function of q plus s2 is a function of t. Then 3 becomes a half of del q s1 square, this s1, minus mu by q plus del s2. This is a function, sum of two functions s1 and s2. S1 is a function is q and s2 is a function of t. So we get del t s2 equal to mu by q minus half del q s1 square. This equals to mu by c, say, where mu is constant. And then this del t is equal to mu by c, so this implies this s2 equal to mu by c plus c into t, equation 5, and this mu by q minus half del q s1 whole square equal to mu by c, this equal to del q s1 whole square equal to 2 into mu by q minus mu by c. So del q s1 equal to this equal to root 2 mu root over of c minus q by c 1 by root q. Integrating, we get s1 equal to integration root 2 mu root over 1 minus q by c dq by root q. Put root q by c equal to sine theta, and then sine square theta equal to q by c, then root q equal to root c sine theta, and cos theta equal to root over 1 minus q by c, and dqc equal to 2 sine theta cos theta d theta. Hence s1 equal to this, after simplification we get this equal to root over twice mu c sine inverse root over q by c plus whole root over twice mu q bracket c minus q whole divided by c. Hence the required solution is this plus mu t by c. This is the s1 and this is the s2, and c is a constant. Next question, question 5d. Define Poisson bracket if fpqt and gpqt are two constants of motion, then show that the Poisson bracket fg is also a constant of motion. A Poisson bracket, the definition is obvious, so do yourself. And second part, the total time derivative of f can be written as ddt of f equal to del tf plus summation k equal to 1 to n del qk f q dot plus del pk f pk dot. Then this equal to this qk dot, this means this del pkh, this, and pk dot equal to minus del qkh. So, and this equals to Poisson bracket the fh with respect to q and p. So this this del tf plus Poisson bracket of f and h is the Hamiltonian. The function f is a constant of motion if ddt of f equal to 0. So this equal to 0. The constant f fg is also constant of motion. So this constant of motion this. And now if the function f does not depend on time explicitly, then del tf equal to 0, and then the condition for f to be constant of motion is obtained to be the Poisson bracket of fh equal to 0. Thus, if f does not depend on the time explicitly and is a constant of motion, its Poisson bracket with the Hamiltonian vanishes. In other words, A function which Poisson bracket with Hamiltonian vanishes is a constant of motion. This result does not depend whether h itself is a constant of motion or not. Also, we have Jacobi's identity. For any three functions f, g, and k of pk and qk, the following relation holds true. This is the Poisson bracket f, comma, Poisson bracket gk plus Poisson bracket of this g, Poisson bracket kf plus Poisson bracket of k and fg, Poisson bracket of fg. This is equal to 0. Put k equal to h. Then the above identity becomes this f, third bracket f, comma, third bracket gh plus third bracket g, third bracket this hf plus h, third bracket fg equal to 0. Now f and g are constant of motion. Then f h equal to 0 and third bracket this Poisson bracket of gh equal to 0. Hence, so this gh equal to 0 and fh is equal to 0. So we find this Poisson bracket of h and Poisson bracket of fg equal to 0, which means that fg is a constant of motion. Thus, the Poisson bracket of two constant of motion is itself a constant of motion, and this is called the Poisson's theorem. This completes the Unit 4 2022. The PDF of this note is given in the description box. Thank you for watching this video.